Hello everyone, welcome to this session. So neural network training is an optimization process based on gradient descent. So as we have seen in the past sessions, this is not a simple optimization problem. So in this session, we will go deeper into it in terms of the optimization quality and the optimization speed or efficiency. So in the past sessions, we have seen that the forward and backward propagations. So we first use the forward propagation to transmit the signals, and then we get the error. Then we back propagate the error to update or optimize the W and B, right? So what we have shown, we used only one training sample. And in the training, we need to consider all the training samples. So then in each iteration, we need to use a number of training samples, multiply for each of them, we need a forward and backward propagation in this optimization. So these together, we call it a one epoch. And we need to do epoch by epoch until the network is trained. It means that the problem is optimized and we get the optimal value of W and B. So this is not a simple or small size optimization problems, especially when the number of training sample is large. So then we have introduced the batch training. So I hope you still remember it, right? So we have talked about it in the second week in the machine learning part. So batch training means that we get some batch and we update the W and B if in neural network by the average logs of the samples. And in many cases, the most popular way is to use a mini batch. So in the following, we will repeat or review the batch training and mini batch training, and we link it to neural network. So we have talked about mini batch gradient descent. We call it MBGD, right? So in batch gradient descent, B or BGD, so all the samples are used together, and we get the average of them, the average gradient of them, to carry out the gradient descent. And all this is SDD, stochastic gradient descent. So in this way, we only use a single sample at a time and use this one to update W and B, right? So MBGT is calling for a balance. So we define a certain number of mini batch. So what is a mini batch? So mini batch is a fixed number of n training samples. So considering the total number of training samples is n, and n is smaller than that, right? So we call the n, that is a batch size. So based on this, so MBGD, we can work as follows. First, we split the training data set with total number of n into a number of mini batches. And each mini batch, we have the size of n, right? Then I use one mini batch as a training set. We get the average of the gradients of this mini batch. Based on this average gradient, we update the W and B, right? Then we will repeat this process to cover all of the batches. So after this, we have one epoch, right? Because we use all the training samples. And then we need to go to epoch by epoch. So this is a whole optimization process. And in MBGD, the hyperparameter is what? Is n, right? So the mini batch size. So if the mini batch size is small, this goes to the stochastic gradient descent. The extreme case is m equals to 1. So when m is large, it goes to the batch gradient descent. So the extreme is that the batch size is n. So normally, often used size is the 32, right? This is I covered more details on this in the second week of the machine learning course. So for more details, you can review that course. So MBGD, the benefit is that it avoids the converting to local optimum to some extent, and we use less memory, as the speed is often fast. So this is how we use the training data to carry out the gradient descent. Not only is this, the gradient descent itself, the optimizer itself, can also be improved. So in the standard gradient descent, the learning rate is universal and unchanged. So what is learning rate? Is a step size in gradient descent, right? So in gradient descent, the two essential elements are the gradient and the learning rate. So the gradient tells which direction should the algorithm go, right? And the learning rate is a step size. So how large is one step? So let's first see this figure, right? Consider we are optimizing the loss function. So if the step size is small, then what it causes is that the learning is too slow, right? Because it's too small to reach this optimum. Not good. If the step size is too large, the thing is opposite. First point here, then it jumps here. Then it jumps here. It keeps jumping, right? This also affects the optimization speed and quality. So the best way is that if we can have the adaptive learning rate, so sometimes we can use a larger step to increase the speed of the optimization, and sometimes we can use small steps, to quickly get to the local refinement. So if we want to get the adaptive learning rate, right, there is an optimizer that is very widely used. We call it the Adam optimizer. So this optimizer, we have adaptive learning rates for different parameters. So this is based on the first and second moments of the gradients. So this algorithm is quite fast and is widely used in the neural network training or this optimization. Also in this optimization, there are some advanced topics. So here I make a general introduction and provide you some examples. So for example, one challenge is vanishing gradients. So this means in some stage of the training, for the layers far from the output layer, the gradients is very small. So this means that it needs to go for a long time, right, to progress the learning. The learning slows down a lot. The vanishing gradient is what we should avoid. And oppositely, we have exploding gradients. So it means it's too large in some layers of the network. So this causes the training to be unstable. It keeps jumping, right? So there are some solutions to avoid these problems. So here I list some. So for example, batch normalization or weight initialization or gradient clipping. So these ones, I won't cover this in this introductory course. So more details, you can find more details from the internet. Okay, so thank you very much for listening. So that's all for this session. Bye-bye.